So yeah, in this video we are going to talk about cross-validation for model evaluation. So we just talked about hyperparameters, and usually cross-validation is very commonly combined with hyperparameter tuning and model selection. However, I think it's first easier to understand how k-fold cross-validation works in a simpler case, namely model evaluation. So we will take a look at some of the properties of k-fold cross-validation before we then later talk about cross-validation for model selection. So yeah, first, like I said, in the first part we will be talking about k-fold cross-validation for model evaluation. Yeah, so this slide shows the concept of k-fold cross-validation quite succinctly. So here that's like the big picture overview. In particular here we have an example of 5-fold cross-validation. So how does that work? So let's say we have a data set. So this is here our data set. And what we do is we split it up into a validation fold and the remainder. So let's use different colors for that. So a validation fold, I can actually use the same color as here, the blue one. Okay, so the validation fold, and then the remaining ones, these 4 chunks here, are the training fold. You combine them into a training fold. And then this is similar to the holdout method. You train the model on the training fold, and then you evaluate it on the validation fold, and then you get a performance for that. And what's different from the holdout method now is that you are rotating the validation folds. So you are then moving over the validation fold to the next chunk here, and you can see there is no overlap between the data points in the validation folds in the first case and now in the second case. So you keep going in each iteration. You pick a different validation fold, so the data points in the validation fold are different. So in that way, you make use of all the data points for evaluation. So if we have 5-fold cross-validation, we will have 5 distinct validation folds, and there will be then 5 iterations. So for each iteration, you compute the performance. If you have 5-fold cross-validation, you will end up with 5 performance measures. And then usually what people do when they report the k-fold performance is they average over all these estimates, so from each round. So you're just averaging over the 5 performance values. So remember, we are talking here about k-fold cross-validation for model evaluation, not selection. So we are not doing any hyperparameter tuning, so no tuning here. And in this case, what we can do is we can actually regard this performance estimate here as an estimate of the generalization performance, instead of just using the holdout method where we split the dataset into a training and a test set. We can actually use that method here to evaluate the performance of the model. However, now let's say you want to use the model in practice. So the problem now is which model are you using in practice, because you have now 5 models here, right? So each model is different. So what you can do is, after evaluating the performance here, is you can train a new model on the whole data set. So here I have the whole data set. So this is all the combined data points here, and I can train a model on that one with a fixed set of hyperparameters, because we said we don't do any tuning. Then we just use some fixed hyperparameters and we fit a model to the whole training set, which is then our model. And that is actually it then. We can have maybe an independent test set still to evaluate the performance of the model, but it's usually not necessary if we don't do any tuning, because this one should already give us a good estimate of the generalization performance. And just to, I see here is point C. So here that's just illustrating how one of the performances is computed. It's one of the rounds here is similar to the 2-way holdout method. because in this round, in each round, we split the data set into a training set and a validation set. Yeah, so here's the summary of the points we talked about. So note that the validation folds are non-overlapping, so that's what I explained, so they are all non-overlapping here, and that all data is utilized for testing. By that I mean not in each round, but if we take a look at that, every point was at some point used for testing or validation. So note that also some people call the validation folds test folds. It doesn't really matter. You can also call them test folds. Another thing though to notice is that the training folds are overlapping, so they are not independent. So they are. So if you take a look at this one, then you can see, for example, in this case, these are overlapping between the two rounds, the ones in green. So in that way they are not independent, right? So if you look at 1 and 2, so the only case where the train data differs is here on this left-hand side, and then you can see that we use overlapping training data for the rounds. Another thing is that makes it hard to estimate the variance from the different training sets. So we can actually take a look at the variance here based on the different performances. So we can take, if we consider this as a distribution, we can take a look at the variance to get an idea of the variance of the model, like related to what we talked about when we talked about the bias variance decomposition, when we had the expectation over the training sets. However, the problem is here there's the overlap, so it's kind of impossible to get an unbiased estimate of the variance. Another thing to notice is that if we make k smaller, the estimate will become more pessimistic. So why is that? So if we make k smaller, we have fewer data points for fitting the model in each round. So consider a case where I have this data set and I only do k-fold, like k equals 3. So then in each round, let's say for this first round, this chunk is for validation, for the second one, this chunk is for validation, and for the last one, this one. So here each chunk is bigger than the chunk here in the 5-fold cross-validation case. So that means that fewer data is available for training, so that related to the fact that we talked about last week, we have a performance estimate that is more pessimistic because we withhold data from fitting. So here's a special case of k-fold cross-validation, namely the case where we set k equals to 2. So just to contrast this with the holdout method, two-fold cross-validation is actually different from the holdout method. So in the holdout method, notice that we divide the data set into a training and a validation or test set. Whereas in two-fold cross-validation, what we do is we divide it exactly in half. Here, for example, it could be 70% and 30% and so forth, or any other number like 90% and 10%. But for two-fold cross-validation here, we split it exactly in the middle, and then we rotate. So we first have this part here for training, and then in the second round we have this one for training. So we have 2 rounds if we have two-fold cross-validation, which is different from the holdout method, because here in the holdout method the split, the proportion is arbitrary, it's not in the middle, and we don't rotate. However, you can think of each round as a special case of the holdout method, where we split it exactly into 2 halves. It's also different from the repeated holdout method. So k-fold cross-validation is different from repeated holdout, because in repeated holdout we randomly split. So we don't have the case where each data point is only used exactly for testing once. So if you consider k-fold cross-validation, each data point is only used exactly once, right, for testing. Because if we would just draw this again, say for 3-fold cross-validation, then this part would be for validation, and then this part would be for validation, and then this part would be for validation, but there is no overlap. So we don't use any data point twice for validation. Each one is only used once. In the repeated holdout method, we randomly divide the data set into a training and a validation set. So in this case, it can happen that in 2 rounds the same data point might be used for testing. So that's also a difference between k-fold cross-validation, where each data point is only used exactly once for testing, compared to the repeated holdout method. So another special case of k-fold cross-validation is when we set k equals to n. So if we set k equals to n, then the data point, so the number of iterations, will be equal to the number of data points. So if we have n data points, we will have n iterations, and the validation set is only consisting of 1 data point. And this is also known as leave one out cross-validation, which is also often abbreviated as LOOCV, leave one out cross-validation. So it's a special case where the validation set only depends or consists of 1 data point. Okay, let's now take a look at the study investigating k-fold cross-validation for model evaluation and comparing it to the holdout method. So to emphasize or to recall, here we are still talking about k-fold cross-validation for model evaluation. So the study was done by Hawkins, Basek, and Mills in 2003. It's like 17 years ago, but it's still kind of relevant. The method is still the same, so even though the study may seem to be a little bit old, the study is still relevant. So let me read out what I copied here from the paper and then explain. So what they say is, where available sample sizes are modest, so think of small data sets, holding back compounds for model testing is ill-advised. So compounds, you can also think of observations. So here the recommendation is that holding out data for testing and not giving the data to the model for fitting is not a good idea, because this fragmentation of the sample harms the calibration, so training, and does not give a trustworthy assessment of the fit anyway. So that comes back to the method when we have a small data set and we divide it into a validation or test set and a training set. Then the problem is we withhold valuable data from the model training, which is what we talked about before. And if the data set is small, the test set will be small anyways, even though we may use a large chunk of the data for testing, and it will not be very reliable anyways. So they say it is better to use all data for the calibration step and check the fit by cross-validation, making sure that cross-validation is carried out correctly. The only motivation to rely on the holdout sample rather than cross-validation would be if there was a reason to think that cross-validation is not trustworthy, for example, biased or highly variable. But neither theoretical results nor the empiric results sketched here give any reason to disbelieve the cross-validation results. So here they are making the case that cross-validation is more reliable than holdout method, so they recommend using the cross-validation method instead of the holdout method. So let's take a look at the experiments that they have done. So here what they have is a bunch of experiments, and for each experiment they report a mean and a standard deviation. So the reported mean refers to the average difference between the true coefficients of determination, R squared. So here they are looking at a regression case, but a similar study could be done for classification. And the coefficients obtained via LOOCV, which is the leave one out cross-validation that we talked before. So these are the Q squared. This is from LOOCV. After repeating this procedure on multiple different 100 example training sets. So they estimated the true determinant of coefficient of determination, for example, from a simulated data set, and then they created 100 example training sets, multiple of these, and compute the mean difference between the true value here and the estimated value. And in this case, they find that the difference is 0.010 in terms of the mean, and the standard deviation is 0.149. Now, this is for LOOCV. Now, these other cases are for the holdout method. So they are holding out either 50 data points, 20 or 10 from the training set. So in rows 2 and 5, the researchers used the holdout method for fitting models to the 100 example training sets. So here, in this case, they only have 50 training examples. Here they have 80 training examples. And here they have 90 training examples. And they evaluated the performance of the holdout set sizes 10. Okay. Each experiment was repeated 75 times, and the mean column shows the average difference between the estimated R2 and the true values. Okay, so here they repeated the experiments 75 times. By the way, it doesn't make sense to repeat that for the leave one out cross-validation, because changing the random seed doesn't really change the leave one out cross-validation, because you still have the same training faults and the same test faults in leave one out cross-validation. There is no random seed in that way. I mean, every data point gets evaluated anyways, so what I mean is, if you have a data set with these different iterations, so each data point gets evaluated exactly once, whether you change the order, let's say you do it this way, or things like that, or you pick this data point first, then this one, and then this one, and then this one. Each data point still gets evaluated exactly once. So for the leave one out cross-validation, it doesn't really matter whether you change the random seed and repeat it, you will always get the same results. Okay, what they then found is that here for that case, the mean is 0.028. So holding out more data for testing still gives us a reliable estimate, but the smaller the holdout data set is, the larger the difference becomes. So you can think of it as the model may become better if we have larger training sets. However, the smaller test sets will cause more unreliable estimates of the performance. You can see the mean increases the smaller the test set becomes, but also the standard deviation between these 75 repetitions increases, so it becomes more unreliable the smaller the holdout set is. So actually here, based on these simulations, you can see that leave one out cross-validation has actually the best properties. Okay, so this was done for regression. Now what about leave one out cross-validation for classification? So there are some problems with that. So while the leave one out cross-validation is almost unbiased, because we almost used a full data set in each round for training the model, one downside of using this method over k-fold cross-validation with k smaller than n is the large variance of the estimate. So for classification, it can result in a large variance, can be related to the fact that some people call the leave one out cross-validation defect for classification, because we have a discontinuous loss function, the 0-1 loss. So what we are doing is we are averaging over the 0-1 loss cases, which is a little bit weird. In the regression case, it makes a little bit more sense, because for each data point, we get a real number prediction. So if we have these different rounds, for each point, we continue like that, for each point we get a continuous value, and then it's easier to average over those instead of, let's say, averaging over 0 and 1s, which is a little bit more weird. So some people also say that leave one out cross-validation has a high variance because the test set only contains one example, so there's a large fluctuation between those even then, because the test set is very small. So small test sets, the smaller the test sets, the larger the variance, because each prediction estimates the true generalization performance not as well as if you would have more samples. It's kind of related when you think of the sample mean distribution, where you divide by the square root of n. The larger the sample size, the more reliable your estimate. In textbooks like The Elements of Statistical Learning, the authors also say with k equals n, the cross-validation estimator is approximately unbiased for the true expected prediction error, but can have a high variance because the n training sets are so similar to another. It's another phrase that people use to say that leave one out cross-validation is not a good idea for classification. But let's take a look at an empirical study and some recommendations by Ron Kohavi. So in this study, Ron Kohavi took a look at k-fold cross-validation and compared it to leave one out cross-validation to make some recommendations which one to use in practice for classification. Also note that for k-fold cross-validation there are the different choices for k. So he also took a look at which k to recommend if k-fold cross-validation turns out to be more useful than leave one out cross-validation for classification. So let's focus on the left-hand side first. So here on the y-axis, that's the prediction accuracy. There are different data sets: soybean, vehicle, I think a random data set, a mushroom data set, and hypo, I forgot what hypo was, and a chest data set. So there are 6 different data sets here. And they looked at the C4.5 algorithm, which you remember is a decision tree algorithm. So now on the x-axis we have the different folds. So here this would be 2-fold cross-validation, 5-fold cross-validation, 10-fold, 20-fold. And if you have negative numbers, that means how many data points were not used for training. So here this one would be leave one out cross-validation, -1. So 1 data point is left out. So this corresponds to the number of data points left out. Whereas this one is the k and k-fold cross-validation here. Okay. Now what we can see here is when we have a very small number of k, so k equals 2, we can see that the performance estimate is very biased, negatively biased. So by the way, I should say the gray bars here, the gray regions indicate 95% confidence intervals for the true accuracies. So here these bars are the true accuracies. Now if you take a look at the 2-fold case here, you can see that this one is pretty far away from this one, and correspondingly I think this one corresponds to this one. And is there another one below there? Yeah, here. So this one is good. But for these two, for soybean and vehicle, but also for mushroom, there are quite substantial differences compared to the true accuracy. So here we have this negative or pessimistic bias. We also see that to some extent for 5, so you can still see there's some difference here. The difference becomes smaller for 10 here, for example. So this is already smaller. And then for a case like, which color? Here, let's use red. For these ones here, for leave one out, for example, you can see it's almost unbiased, which is good. So for leave one out, we have almost an unbiased performance estimate. However, the problem is that it can have a high variance. So empirically, you can see here on the right hand side estimating the variance. So here we are looking at the standard error of the mean or confidence intervals, whereas on the right hand side we look at the variance, so the variance across the folds. And then so here it's the square root of the variance, but you can see that the estimate varies more if we would repeat that procedure for different training sets, where the expectation is over the training sets. Here they are looking at the standard deviation of accuracy of the population, and it's the square root of the variance, and you can see that the variance is large for very small numbers of k. For two-fold k, for two-fold cross-validation, there's a very large variance or standard deviation, and you can also see that for the leave one out cross-validation. However, for other values like especially 10 here, for 10 there's a small variance, so this one is more reliable. So if you repeat that on different training sets, so the variance of this estimate is smaller compared to small case or large case. And again, going back here to the left hand side, this also has a relatively small bias. So in practice, based on this paper, Ron Kohavi's recommendation is to use tenfold cross-validation in practice. That's one that he recommends, and also many machine learning practitioners recommend in practice, compared to using leave one out cross-validation or fivefold cross-validation. However, if you have a very, very large data set, then fivefold cross-validation may also be fine. And if you have a very, very small data set, then tenfold may not even be enough. Then maybe leave one out cross-validation is a good idea. So it always also depends on the data set, but as a rule of thumb, tenfold is actually a good compromise. Now, summarizing k-fold cross-validation for model evaluation. So what happens if we increase k? So this is something we can answer based on the empirical studies that we just looked at. And so, for example, one question would be the bias of the performance estimator increases or decreases, or is more accurate, more variable. So the other one would be the variance of the performance estimators increases or decreases when we increase k. And instead of answering that for you, I think this would be actually a cool little quiz. So I will actually post these questions on Piazza, so as a little self-assessment exercise from the empirical studies that we just took a look at. Okay, so I will post that as a quiz on Piazza for you. And in the next video we will talk about cross-validation for model evaluation in practice using some code examples using scikit-learn.